all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about linear classification models and LDA, linear discriminant analysis. Learning linear classification models and linear discriminant analysis is essential for anyone working in data science, machine learning, or pattern recognition, as they form the foundation for solving classification problems. Linear classifiers offers a simple, efficient, and interpretable method for separating data into categories, especially when the data is linearly separable. And in LDA, on the other hand, enhances the classification performances by projecting data into a lower dimensional space while maximizing class separability. This is not only reduces computational complexity but also improves accuracy by removing irrelevant features and noises. Understanding these techniques is very important for building robust models that generalizes well and for pre-processing data in more complex and machine learning pipelines. We'll see one by one. First, the introduction to linear classification models. So if you are taking the classification algorithm, it works by learning the functions that can separate different classes in data based on linear predictor. This predictor combines input features using a set of learned weights. In a linear classification model, these weights are used with the feature vectors to make predictions. The result is a score or value that helps decide which class a new data point belongs to. The core of a linear classification is a linear combination of inputs. This means each feature is multiplied by a weight and all the results are summed. The outcome determines the predicted class. The weights of the model are adjusted during training to reflect the characteristics that define each class, helping the classifier to generalize well on the new data. However, in the linear classification, simply we can say if you are taking the AND gate, OR gate, or some other gates, we can able to separate the positive values, that is true values, with the positive values with the linear line. But as far as the XOR gate is considered, if two input XOR gate, if you are taking, will give the input features as 0 0 0 1 1 0 1 1. So the outputs are for 0 0 and 1 1. We are getting the value, it is 0, and for 0 1 1 0 the output value is the 0 0 1 1 the output value is 0, and 1 0 0 1 the output value is 1. So if you wanted to separate, we are going for more than 2 lines for the separation. So however, a major limitation is that the linear classifiers cannot model relationships that are not linearly separable, such as the XOR logic function, which requires a nonlinear boundary. Next, what is linear classifier and what it can do and it cannot do? That we'll see. Linear classifiers perform well on problems where data can be separated by a straight line or plane. These include linearly separable data sets with clearly defined boundaries. And they are efficient and easy to implement for straightforward problems with the clear divisions between classes. On the other hand, they are ineffective when the data has complex nonlinear boundaries, such as in the case of circular or spiral class distributions. A well-known example of limitation is their inability to solve XOR problems where class separation require nonlinear approach. Next, we'll go into discriminant analysis. First, we'll see the overview of discriminant functions. LDA. LDA stands for linear discriminant analysis. It is a supervised algorithm that needs labeled data to find a linear function that separates different classes. It is widely used for tasks such as dimensionality reduction, where the goal is to reduce the number of features while preserving class separability. And LDA is often a pre-processing step in pattern recognition systems, helping other classifiers perform better by projecting data into a more meaningful space. It works by finding the decision boundary that maximizes class separation, making it easier to distinguish between classes. And what are all the objectives of LDA, linear discriminant analysis? This LDA aims to find a linear or plane, a line or a plane that can separate data points of different classes in a way that enhances classification accuracy. This separation is achieved by maximizing the distance between the means of the different classes, ensuring they are far apart in the new space. At the same time, it minimizes the variance within each class so that the data points within a class are closely clustered. The Fisher criterion is used to balance these two goals, creating a decision boundary that is both wide between classes and tight within classes. Next, how LDA works. Step by step, we'll see it. The process begins with by calculating the mean and standard deviation of each feature in a data set, helping to summarize the class distributions. Next, we have to calculate two types of scatter matrices or computer. Within class scatter, that is how much data spreads inside each class, and between class scatter, that is how far apart the class means are. These matrices are used to compute eigenvectors and eigenvalues, both the things we are finding out, which captures the directions and magnitudes of maximum separation. The top k eigenvalues vectors corresponding to the largest eigenvalue are selected to form a transformation matrix focusing on direction of maximum class separation. This matrix is then used to project the original data into a new space with fewer dimensions but better separation between classes. Finally, the transformed data can be used for classification or further analysis, now existing in a space where each classes are more easily distinguishable. Next, if you are looking into this two graphs, this visualization of class separation, first before applying LDA, the features are like this. After applying, we can able to discriminate the two different features like this by using the linear line. In a typical LDA visualization, class distributions are shown in their original feature space, which may overlap or appear poorly separated. Here we cannot able to separate with this feature, this round features with this triangle features. LDA applies its transformation to move these classes into a new space where the separation between them is more distinct. So if you are looking into this, you can able to identify. This visual representation helps in understanding how LDA improves the class distinction, especially in case of overlapping data. The final result is a pilot or graph where the clear boundary, that is, a final result is a plot or a graph where a clear boundary or line divides the transformed classes of data, enabling more accurate classification. So we can able to classify this blue color into one line and the another. So few data may be coming into this side. So what are all the benefits of using LDA? LDA is highly useful for classification problems because it improves the decision boundary between the classes by reducing the overlap. So if you are looking into this graph, before applying LDA, there may be lot of overlapping. But after applying this LDA techniques, we can able to reduce the overlapping. And also it also serves as a dimensionality reduction technique, which can help to reduce computation time and improve model performance. LDA is particularly effective with high dimensional datasets where other algorithms struggle due to data sparsity and or overfitting. Yeah, unlike many machine learning techniques, LDA is less affected by the curse of dimensionality, making it a robust choice for large feature spaces. And coming into the conclusion, the linear classifiers are efficient and interpretable models for classification, especially when data is linearly separable. However, this simplicity can be a limitation in handling complex data sets with nonlinear boundaries. And LDA extends the capabilities of linear classifiers by transforming data into a space where classes are more separable. This transformation enhances both classification performance and model interpretability, making LDA a valuable tool in modern machine learning pipelines.